Welcome to the Deep Dive. For your deep dive today, we've explored some really fascinating material, including recent theoretical papers on motion theory, and we're going to unpack its, well, elegant reinterpretation of Albert Einstein's universe.
It's quite a perspective shift.
It really is. So, to kick us off, let's revisit a classic thought experiment. It just brilliantly captures the essence of his genius, doesn't it?
The train one.
Yeah, the train and the lightning. Imagine a high-speed train, right? Racing through the night.
Okay.
Two lightning bolts strike the tracks simultaneously, one in front, one behind. Now, if you're standing on the embankment watching...
See them hit at the exact same time, simultaneous.
Exactly. But for a passenger inside that speeding train...
The front one looks like it strikes first.
Right. And here's the kicker. Neither observer is wrong. No one's lying.
It's not an illusion.
No. Reality itself just sort of shifted the rules of at the same time. It's this mind-bending paradox that's our gateway into understanding how Einstein, well, he didn't just describe motion.
He showed motion dictates things. It runs the clocks, shapes the rulers.
Writes the fundamental script for reality. It's incredible.
It really is a foundational insight. I mean, for centuries, we just assumed a universal now for everyone.
Took it for granted.
Completely. Einstein just shattered that. And what's truly profound is how that simple scenario reveals that our perception, no, our experience of time and space is inherently interwoven with how we move.
And that's where we take our deep dive today. We're going beyond Einstein's original, groundbreaking geometry.
Which was revolutionary in itself.
Oh, absolutely. But we're exploring a new interpretation, motion theory. This framework translates what Einstein described with geometry and invariance.
The things that don't change for different observers.
Exactly. It translates those into the synchronization behavior of structured motion loops. Think of these loops as like fundamental patterns of motion.
From tiny particles all the way up to cosmic structure.
Yeah, all interacting and sort of trying to keep time together.
Right. So we're essentially asking, what if the geometry, space-time itself, isn't the fundamental thing?
What if it emerges?
Exactly. What if it's an emergent property of how things manage to synchronize, how they keep the beat together?
So get ready, because we're going to revisit Einstein's greatest hits, not just as history.
No, as these huge shifts in understanding.
Right. And then we'll see how motion theory offers this deeper, maybe more rhythmic score to the universe, and how it aligns with and maybe even extends Einstein's vision.
Sounds good. Where do we start?
Okay, let's set the stage. A quick but, impactful tour through Einstein's brilliance. His miracle year, 1905.
Right.
It was just astounding.
Unbelievable, really.
He gave us special relativity beyond just the constant speed of light. What was the most revolutionary implication for how we see reality?
Oh, definitely the complete dissolution of absolute simultaneity. And tied to that, the idea that space and time weren't absolute backdrops.
They became relative.
Dynamic. Exactly. Before Einstein, it was just unthinkable that two events could be simultaneous for me, but not for you if you were moving differently.
Yeah.
Special relativity shows that time dilation, clocks ticking slower for moving observers, and length contraction objects getting shorter in their direction of motion aren't just, like, perspective tricks.
They're real transformations of space-time itself, based on velocity.
Right. It fundamentally rewove the fabric of reality.
And he didn't stop there in 1905. I mean, he kept dismantling classical physics, didn't he, brick by brick?
He really did. That same year, his work on the photoelectric effect. Absolutely critical. Photons. It showed light isn't just a wave. It arrives in these discrete packets, these quanta of energy.
Which wasn't just a curiosity, right?
Not at all. It revealed that matter absorbs and emits energy in specific quantifiable chunks. It laid a massive cornerstone for quantum mechanics.
Wow. And Brownian motion.
Ah, yes. Finally proving atoms and molecules were real, explaining that random jitter of tiny particles you see under a microscope. It settled a huge debate.
Incredible. So much in just 1 year. And then, of course, the equation everyone knows, even if they don't know what it means. EMAMC.
Yeah, ICOM, yeah.
What was the real paradigm shift behind that? More than just a formula.
Oh, it was profound. It revealed that mass, the very stuff we think of as solid,
is just energy.
It's congealed energy, energy bound up, capable of immense release. Think nuclear power stars.
It all comes back to that.
It does. It showed mass and energy are two sides of the same coin, fundamentally linked, transmutable.
So if 1905 was the warm-up, you could say 1915 was the main event. General relativity, how did that completely redefine gravity?
General relativity. I mean, it's a masterpiece. It threw out Newton's idea of gravity as some mysterious force pulling things.
Action at a distance.
Right. Instead, Einstein said gravity is the curvature of spacetime itself.
So matter and energy warp spacetime.
And that warped spacetime tells matter and energy how to move. Free fall isn't being pulled. It's following the straightest possible path, a geodesic through that curved geometry.
It's just...
It is. It replaced an instantaneous force with this dynamic, geometric explanation.
And his later work just kept pushing the cosmological, constant, gravitational redshift, light bending, gravitational waves.
All predicted by general relativity.
And he even grappled with quantum theory through the EPR paradox, questioning its completeness. He never stopped searching.
Relentless. And through it all, what Einstein was really doing, fundamentally, was translating the world into a language of invariance.
Things that stay the same no matter how you look at them.
Exactly. And this is where our sources on motion theory come in. They suggest reading that very language, those invariants, as the rhythm sheet.
The sheet music.
Kind of. The instructions for how these loops of motion keep time together, or, how they fail to synchronize.
That's a really fascinating way to frame it. Okay, so we've done the lightning tour of Einstein's breakthroughs. Let's dive into how motion theory reimagines special relativity. It starts with c, the speed of light, being constant for everyone.
The bedrock postulate.
And Minkowski gave us that 4D spacetime picture. So how does motion theory reinterpret something like time dilation using its rhythm idea?
Okay, so motion theory sees time dilation not just as time slowing down, but as a system's internal rhythm slowing relative to another, because it's, let's call it a relative phase advance budget, is being spent elsewhere.
A budget, like an allowance.
Sort of.
Yeah.
Think of it like you have a fixed budget for maintaining your internal clock's tick and for moving through space. If you spend a lot of that budget on translation moving really fast, you have less budget left over for your internal clock to tick at its usual rate.
Ah, so you can't spend the same phase on going fast and ticking fast.
Precisely. So the internal rhythm, what we perceive as the flow of time for that moving object, appears to slow down compared to someone stationary.
That concept of a phase advance budget, that actually makes a lot of intuitive sense. Okay, so if that's time dilation, how does this rhythmic idea explain length contraction? What's happening to the beat when an object seems to shrink?
Right, length contraction. From this perspective, it happens because the phase spacing, the kind of rhythmic distance between points defining the object's length, shrinks along the direction of motion for that fast observer.
The spacing shrinks.
Yeah. Essentially, the loop's internal standing pattern, the rhythm that defines its structure, squeezes in the direction it's moving. It has to maintain synchronous propagation to keep everything internally coordinated at speed c. The patterns adapt.
So it's not like the object is crushed, but its internal rhythm adjusts, making its measured length appear contracted along the motion axis. And the relativity of simultaneity, the whole no universal sync line thing.
It fits right in. It basically means what looks simultaneous to you might not look simultaneous to me, because there is no universal metronome, no universal sync line.
It depends on how you're synced up locally.
Exactly. It depends fundamentally on how your local motion loop, your system, has negotiated its phase relationship with the background. Everyone's synchronizing locally, and those local syncs just don't necessarily align across the board.
Okay. And that invariant interval, the space-time distance that Einstein found, everyone agrees on.
Motion theory sees that as the phase distance between events. It's like the fundamental beat count that remains constant, no matter how you slice up space and time.
So Einstein used geometry to explain these effects. What's the really fundamental shift motion theory is proposing here? Is it just a different description?
This is where it gets really interesting and maybe a bit controversial. Einstein's math brilliantly describes how space-time behaves, the geometry. But motion theory flips it. It suggests that the underlying synchronization rules produce the geometry.
Wait, so geometry isn't fundamental, it's emergent.
That's the proposal. What if geometry is an emergent property arising from the way these fundamental motion loops synchronize, or fail to synchronize? It puts the rhythm, the synchronization, first, and says the geometric structure we observe comes from that.
Wow, okay, that is a profound reorientation. So if special relativity is about phase and sync in, sort of, flat space-time, let's move to the big one. General relativity, Einstein's masterpiece. How does motion theory interpret gravity?
Right, general relativity. Einstein's equivalence principle, acceleration and gravity feeling the same locally, was brilliant.
And matter tells space-time how to curve. Curvature tells matter how to move.
Exactly. Motion theory translates this into a sync-centric view. It defines gravity itself as a gradient in synchronization density.
A gradient in sync density, what does that mean?
Imagine spacetime, or the substrate, as a medium where rhythms propagate. Near a massive object, near concentrated energy, the local rhythms run slower. The ability to synchronize is denser, you could say.
Okay.
So world lines, the paths objects take, naturally bend towards regions where they can advance their phase with less conflict, less strain. The geodesic, the straightest path in GR,
becomes the least phase strain path.
that's the idea. It's like a dancer intuitively finding the easiest way to move across a floor where the rhythm keeps changing from spot to spot.
Okay, that makes sense. So gravitational redshift clocks deeper in a gravity well, ticking slower.
Isn't just time slowing down in the abstract? It's those clocks accumulating less phase, a slower beat count per unit of time measured far away, and light climbing out.
It loses frequency? It gets redder?
Because it has to pay the gradient. It's like a rhythm tax. It expends some of its internal rhythm, its frequency, to climb out of that deep sync well.
I like that, a rhythm tax. And light bending around stars, the Eddington experiment result, not a force pulling photons sideways.
Not a force in the traditional sense, no. Instead, the light's phase front follows the sync gradient of the medium. Think of it like light bending when it enters water refraction.
An index of refraction.
Exactly. But here, the refractive index isn't set by a material. It's set by the local mass energy, which dictates the local think density or synchronization speed. The light just follows the path of least resistance for its phase propagation.
Okay. And this should also apply to gravitational waves, right? The ripples LIGO and the others are detecting.
Absolutely. Motion theory describes those as ripples in phase alignment. They're propagating disturbances, deformations in the background synchronization field.
Stretching and squeezing space.
Or rather, stretching and squeezing the phase relationships, the synchronization vectors, between points. It produces exactly that quadrupole pattern LIGO sees. We're basically hearing phase storms echoing from colliding black holes.
Phase storms. It's incredible how this provides a narrative, a rhythmic story, for Einstein's math. He used the metric, GU, the Einstein tensor, GIN, powerful tools describing spacetime's behavior.
Right. And motion theory's insight here is that those same mathematical objects, the metric and the tensor, can be interpreted as describing how easy or hard it is for loops to keep a steady beat from place to place.
So the metric isn't just about distance, it's about the local phase budget.
In a sense, yes. It connects the geometry directly to these fundamental synchronization principles. It gives a dynamic, rhythmic meaning to the equations themselves.
Speaking of deep insights, let's touch on quantum foundations. Einstein, ironically, helped launch it all with photons and proving atoms exist.
Yeah, Brownian motion.
But then he famously resisted quantum weirdness. God does not play dice.
His famous objection to indeterminacy, and the EPR paper arguing quantum mechanics was incomplete.
Only for experiments decades later to confirm entanglement is very real. Spooky action at a distance. How does motion theory view entanglement?
That's a huge question, obviously. Motion theory offers a different angle. It sees entanglement not as spooky action, but as shared loop bookkeeping.
Shared bookkeeping.
Yeah. When two particles, say, become entangled, they're prepared in such a way that they become effectively one higher-order motion loop. Their internal rhythms are intrinsically linked.
Even when they fly apart.
Even then. The correlations we measure later are the residue of past synchronization. They're global phase constraints, shared rhythmic properties that persist even across vast distances. They're still part of the same interconnected rhythm.
Like a shared musical phrase that echoes between two instruments even after they've moved apart. That's a much less spooky way to think about it.
It tries to ground it in these synchronization dynamics.
Okay. And IMCO, mass energy equivalence. What is mass in this rhythmic picture?
Motion theory defines mass as sync inertia.
Sync inertia, like resistance to rhythm changes.
Exactly. It's a measure of how hard it is to rephase a loop to change its synchronization state. The more energy is locked up in a system's internal cycles, binding energy in a nucleus, confinement energy holding quarks together.
The harder it is to change its overall rhythm.
Right. The more that loop resists changes in its frequency or its sync state. So when you convert that internal binding rhythm into traveling rhythm, like in fusion or fission,
you release huge amounts of energy.
You cash out an enormous phase budget as radiant motion, as light and heat. That's the sun-shining converting mass, that locked-in sync inertia into this incredible outpouring of energy by shifting synchronization states.
This whole framework just paints such a vivid, almost musical picture of physics. But the crucial test, How does it stack up against the experiments that already confirm Einstein's theories so precisely?
That's the key question, right?
Hmm.
And it holds up remarkably well by providing a different narrative for the same predictions. Take Mercury's orbit, the perihelion precession.
That tiny shift, 43 arcseconds per century, that Newtonian gravity couldn't explain, but GR nailed.
Motion theory sees that as the predictable beat slip that happens when an orbiting loop moves through a non-Euclidean sync field. The sun's gravity creates a gradient in sync density, and the planet's orbital loop subtly loses or gains phase each time around, causing the orbit to precess. It matches the GR calculation.
Okay, and the 1919 Eddington experiment, starlight bending around the sun.
Motion theory reads that as the light's phase fronts bending because they're passing through an index gradient of the sync medium, like we discussed, refraction, but the index is set by the sun's mass energy, creating a varying sync density. Same prediction, different story.
Even GPS.
Yeah. GPS has to account for both special relativistic effects, the satellite's speed, and general relativistic effects, Earth's gravity well.
Time runs differently for the satellites.
Exactly. Motion theory explains this as engineers meticulously adjusting for different phase rates, influenced by two distinct sync gradients, one due to velocity, one due to gravity. They're literally tuning clocks based on local rhythm conditions.
And the gravitational waves from LIGO, Virgo, KAGRA.
Those phase storms we talked about. Ripples in phase alignment. Again, Einstein's equations predict what we detect, the pattern. Motion theory offers a narrative for how that beat travels, how synchronization patterns propagate.
It really is like having the sheet music for Einstein's symphony.
Yeah.
Okay, but where does this perspective push beyond Einstein? Where does it try to answer the why questions he often left as postulates?
That's where it gets potentially predictive. For instance, Einstein postulated that c, the speed of light, is invariant, a fundamental constant.
Right.
Motion theory doesn't just postulate it. It attributes c to being the maximum synchronization rate that the underlying background, the substrate, allows. There's a fundamental speed limit on how fast phase information can concurrently propagate.
Interesting. So C isn't just a number, it's a property of the medium's ability to synchronize.
That's the interpretation, and spacetime itself. For Einstein, it was this smooth, differentiable manifold, a geometric stage.
For motion theory.
It's seen as the flow of allowed phase relations between all these motion loops. Geometry becomes the shadow of deep motion bookkeeping. The manifold is a great description of the shadow, but motion theory is looking for the projector, the underlying dynamic process.
And the quest for a unified theory. Einstein searched for a unified field theory.
Motion theory takes a different approach. It tends to view fields themselves, like electromagnetic or gravitational fields, as coarse-grained views of the collective behavior of countless microscopic loops.
So unification wouldn't be finding one master field equation.
It might look more like finding a unified synchronization protocol, a single set of rules for how all types of loops interact and keep time, from which the behaviors we label as different forces emerge.
This reframing even touches black holes and dark energy, right?
It does. Einstein's GR gives us event horizons and singularities. Motion theory offers a different lens. The event horizon could be viewed as a point of saturation of sync density.
A saturation.
Meaning, beyond that boundary, there's simply no capacity left for outward propagating phase information. Independent synchronization with the outside universe breaks down. Inside, maybe loops are forced into a collapse of independent timing altogether.
And the cosmological constant. Einstein's blender turned dark energy.
Motion theory might interpret that as the rest tension of the substrate, a kind of baseline, small positive bias in the universal phase budget. When there isn't enough matter and energy clumping together to counteract it locally, this inherent sync tension drives the large-scale expansion of the universe.
You know, thinking about Einstein, his whole career was this deep pursuit of a coherent universe. Simple principles, elegance, no privileged observers.
Beauty as a guide.
Exactly. And his famous distrust of randomness, the God does not play dice line. It wasn't just stubbornness, was it? It was a deep faith that order must be deeper than dice.
Absolutely. And motion theory really resonates with that spirit, doesn't it?
Yeah.
It suggests that maybe what looks like randomness, like quantum chance, is often just unresolved synchronization.
Like we're not seeing the whole rhythmic pattern yet.
Exactly. If you could somehow complete the loop, resolve the phase relationships, the underlying deterministic pattern might emerge. It's searching for that deeper order in the rhythm.
So this isn't just philosophy. It's not just redescribing things. Does it suggest concrete, testable predictions, new ways to actually do physics?
That's the goal. And yes, the framework does point towards some fascinating, though challenging, experimental avenues. One idea is phase index tomography of gravity.
Phase index tomography, like medical imaging, but for gravity's rhythm.
Kind of. Treat the gravitational potential not just as curvature, but as an effective refractive index for phase fronts. Use ultra-precise tools like optical clocks or atom interferometers.
The most sensitive measurement devices we have.
Right? Use them to map tiny phase delays, which are equivalent to the metric potentials. You could map the sync gradient around a mountain, or maybe even detect hidden structures underground by how they subtly alter the local gravitational rhythm.
Wow, that would be incredible. Mapping local gravity by its effect on phase. What else?
Another direction is looking for coherence-limited C tests. If C is related to the maximum coherent synchronization rate.
Could we subtly change that rate?
Maybe. By carefully varying the background coherence, things like the temperature of vacuum fluctuations in a special cavity, or using engineered metamaterials that interact with the quantum vacuum, could we see tiny, tiny shifts in the effective local maximum sync rate.
Without violating all the known tests that show C is constant.
That's the challenge. It would have to be incredibly subtle, perhaps dependent on the coherence of the probe itself, but it's a theoretical possibility this framework opens up.
And lab analogs, making mini-universes.
Sort of. Gravitoacoustic analogs. We can create systems like Bose-Einstein condensates.
Where atoms act like one big wave.
Exactly, or complex photonic lattices. In these systems, we can engineer sync gradients regions where the speed of sound or light propagation varies in controlled ways that mathematically mimic spacetime curvature.
So you could study things like black hole horizons in the lab.
Potentially.
Yeah.
You could study phenomena analogous to Hawking radiation horizon thermality, perhaps by measuring the phase noise statistics in these engineered sync gradients. It connects GR concepts to condensed matter physics in a new way.
What a journey we've taken. From lightning striking a train
To the sync gradients around black holes.
to potential lab tests mapping gravity's rhythm. It really brings to mind that analogy from the source material, the violinist.
Ah, yes, the violin.
The note you hear isn't just the wood or the wire, it's the agreement, the synchronization between the bow's friction, the string's tension, the air's vibration.
It's a perfect image for Einstein's universe. He taught us the universe is that violin. When you move relative to it, the perceived pitch changes. That's relativity. Near a massive object, it's like the air thickens, altering the resonance. That's gravity.
And for light, the fundamental frequency, the beat, never breaks. That's C.
Right. And motion theory adds this intriguing layer. Beneath the wood and varnish beneath the geometry, there might be a deeper score. These fundamental synchronization rules.
Rules that make geometry, energy, even time itself emerge not as static marble, but as dynamic music.
It suggests it was always motion, fundamentally. Einstein taught that motion sets the tempo. Motion theory is trying to write the underlying notation.
And that leaves us and you with a really provocative thought to mull over.
What if the deepest secrets of reality aren't ultimately about forces or fields or even geometry, but about perfect timing, about the universe keeping the beat?
Indeed. What will you discover in the universe's secret score? Thank you for joining us on this deep dive.
See you next time.